let us start this lecture with a thought process from Peter Theodor Landsberg, who says that it has been suggested that thermodynamic irreversibility is due to cosmological expansion. Is it really so or not, is a questionable thing, because we do not know that whether that is the cause or some other things. So, in the last lecture we basically discussing about irreversibilities, and we have seen that irreversibility is inevitable. However, one can minimize the irreversibility to improve the thermal efficiency and or efficiency of a cycle or a system and other things. So, what we will do today, we will be basically looking at the Carnot cycle. So, according to the second law of thermodynamics, the thermal efficiency cannot be really equal to the 100%, but it can be, it must be less than the 100% efficiency kind of things, right. So, therefore, if you look at that, it is always will be less than less than 100% for all heat engines, whatever it is. So, this it cannot be really equal to 100%. So, what is the most efficient cycle we can have? Because we know we are interested to have a heat engine, and heat engine is cycling operating device. So, we always should know that what is the most efficient heat engine we can have, and such that we can achieve the maximum thermal efficiency. And it is possible only if the processes involved in the heat engine should be reversible, then only it will be possible. So, these ideas is basically used by Nicholas Carnot in 1824, who was considered to be the father of thermodynamics, and and he proposed a cycle, thermodynamic cycle, which is known as the Carnot cycle. And this Carnot cycle consists of two reversible processes. One is isothermal reversible process, other is adiabatic reversible process, right. And of course, if you look at these are the two processes, but however, to complete the cycle, you should have two reversible isothermal processes and two adiabatic processes. That means total 4 processes will be there. So, let us now consider a heat engine which is being operated between the two temperature source and sink, and the source temperature is TH, and we are saying high temperature, and the sink temperature will be lower, we are calling it as a TL. So, let us consider a engine like a piston cylinder arrangement here, as I have shown here, and these are all insulated, and there is no friction between the piston and the cylinder surface. This is again hypothetical, like in real situation it won't be, and except the lower portion which is in contact with the thermal reservoir, and some heat will be transferred to this gas, if it is a gas here and we are having a system. And this if you look at, like we are as making it such that the gradient is very, very small, that is the one we are saying, so that it will be reversible. And then what will happen when the heat being transferred to this gas, then the pressure also will go up, so that piston will move, but that again the pressure whatever is acting, let us say if it is pressure here, and then here the pressure will be acting P minus dP, and this is very very small. So, that of course, to keep this gas constant temperature, so that the piston will move up, or there will be expansion, it will go from state 1 to the state 2, keeping the temperature of the gas constant. So, that we call it as a basically the isothermal expansion kind of things, right. The piston will be moving over here. Right. So, this process, we can call it as a basically reversible isothermal process, and if I will bring it, I can bring this system from the state 2 the state 1, and if I do in a very slow manner and there is no irreversibility, so therefore, it can come back. Let us say that after this, what will happen? This thermal reservoir, which was here earlier, being removed, and this is being insulated. Earlier this portion cylinder is insulated, all are insulated, now only lower portion also insulated. And the piston will move from state 2 to the state 3, expansion will be taking place. As a result, the temperature, which was at a higher temperature, which was equal to the thermal reservoir temperature, and that drops down to TL, is the lower temperature, right. And as a result, there will be some isentropic expansion, because it is adiabatic and there is no reversibility in this. So, therefore, this expansion we call it as a basically isentropic expansion process, right. And if you look at like what we will have to do, that we will have to now compress these things, such that what will happen, again we will remove this what we call insulation from the top of the cylinder, and then bring this, the bottom of the cylinder will be brought in contact with the thermal reservoir, such that when it is compressing, that means it is coming from state 2 the state 4 slower manner, that temperature will go up, but however some heat transfer will be taking place to this from this gas, this is your gas, right. This is my system to start with, and then like it will be from state to 3. So, that the temperature will be remaining constant, and this process is basically isothermal compression, right. And you keep in mind that if I want to go back from 4 to 1, and that is possible, like I can go back. So, therefore, it is a reversible isothermal process. And now this again the thermal reservoir is being removed, and then bottom of the cylinder is insulated, and the piston will move from state 4 to the state 1, such that what you call temperature will be increased from TL, that is the lower temperature, to the higher temperature. And there is no heat transfer is taking place, because heat transfer is 0 here, and it is a reversible process. Therefore, this process is basically isentropic compression process. That means, we started with from the state 1, right, and we have returned back to the state 1 again, undergoing the, if you look at isothermal expansion, adiabatic expansion, then followed by isothermal compression and isentropic compression process. That means, a total 4 processes, 2 isothermal what you call compression and expansion, 2 isentropic compression and expansion, right. Basically, that together isentropic compression and isentropic expansion, there are 2 processes, right. So, if you put that thing in a PV diagram, right. So, if you look at, we are here state 1 and this is your reversible isothermal expansion is taking place while keeping the temperature constant, which is same as that of your what you call source or the high temperature thermal reservoir. As a result, some heat being taken from the thermal reservoir, that is QH, and after this then there will be the system will be undergoing a process what you call the isentropic process, like from station 2 to station 3. Of course, the temperature is changing, but there is no heat transfer taking place between the system and surrounding, right. Now, if I want to, if you look at the work done, this process will be what? This portion 1 to 2 and 3, this is my work done. If I look at, this is my work done, isn't it? Some work being what you call done because by the system is expansion. So, work is being done by the gas on its surrounding, right. Now, if I want, I say look, it is a reversible process. Instead of here in this process, can I not go back here? If I will go back here, what will happen? This work is what you call will be nullified, and similarly if I go. So, therefore, we need to take this what you call from station 3 to station 4, that is your isothermal what you call compression process, in which I will have to the system will be giving certain amount of heat to the sink, that is QL, and after this there will be what you call isentropic, again compression will be taking place from state 4 to state 1. So, this is the work like if you look at heat is given, some work input will be given to the what you call by the surrounding to the system, because work is done on the system, right, not by the system, on the system. So, this is the amount of work which you need to supply, that is 1, 4 and 3. This amount of work you will have to supply, and 1, 2 and 3 this work of being produced by the engine. So, therefore, what will be the net work done here? Net work done, if you look at, we know that net work done will be QH minus QL. Am I right? Because heat is coming in and then is being rejected, and that is the work done. So, this is the engine. Why? This is the engine, like what we call is basically Carnot heat engine, because this is a hypothetical engine, right. It is not that it has been produced, but it is a hypothetical engine which will give you a benchmark to check how good it is the other engine with reference to the Carnot engine. Now, I can think of a process in a reverse way, right. Reverse way in the sense, like instead of starting with the station 1, what I will do, I will just expand, right, from station 1 to station 2, right. And then it will be again I will go from state 2 to the state 3, so that I will take some amount of heat from the sink, that is the low temperature thermal reservoir QL, and then I can move from state 3 to the state 1 to again isentropic compression process, right, and from the state 4 to state 1 I can go what you call with the isothermal compression process, while taking rejecting the amount of heat to the high thermal reservoir that we call it a source, that is QL. So, this cycle is known as the what you call reverse Carnot cycle, and this will be representing a reverse or known as Carnot refrigeration system, right, one can think of. So, if you look at these are the process, and what we will be doing now, we will be applying this what you call first law of thermodynamics and finding out the efficiencies and thermal efficiency, what it would be for a Carnot engine. So, by the definition, like we know the thermal efficiency is basically what you call W, that is the net, this is the net work. That means work is produced by the engine and also work is being supplied to the engine. Net engine will be nothing but QH minus QL divided by the QH, and that will give me the thermal efficiency. And as I told, so the QH is the heat absorbed by the Carnot engine and QL is the heat rejected by the Carnot engine. And if you look at this isothermal expansion process between the station 1 and 2, in this case the temperature is remaining constant, therefore dt is 0. And what is happening here? That means, if I apply this first law of thermodynamics, that is du is equal to dq minus dw. You keep in mind that we are using a controlled mass system, right, kind of things. Rather, we are using a controlled mass system. So, then for this process is isothermal. So, therefore, this will be 0, right, is not it? Temperature is not changing. So, therefore, the du, change in internal energy, will be 0. So, then that will be dq is equal to dw. And for this process, nothing but dq is what? Q12, and which is nothing but the amount of heat which is absorbed from the what you call source, and that is equal to the work done 1 to 2, and we know there is a PdV work. So, that will be PdV when I integrate between station 1 to 2, right, and you can assume the ideal gas law, right, ideal gas law we know that P V is equal to R T, right. V is the specific volume, right, and instead of P I can put this R T by V here, and then integrate that, I will get R T1 ln V2 by V1, and T1 is nothing but your TH, right, because this is the TH, right. So, that is the work done is equal to RTH ln V2 by V1, right. So, let us consider the isothermal compression process, that is what you call 3 to 4, right. This is basically we are considering 3 to 4 here, and that is again same way I can write down that Q34 is equal to RTL ln V3 by V4, and which is equal to basically W34, right. And for isentropic process for both the what you call system 2 to 3 and 4 to 1, right, 4 to 1, the dq is 0. So, therefore, q23 is equal to q41 is equal to 0. So, according to the first law of thermodynamics, then we can write down the cycle integral of work is cycle integral q is nothing but q12 plus q23 plus q34 plus q41. I mean, you go this way, 1 to 2, 2 to 3, 3 to 4, 4 to 1, and we know that this is basically, if you look at q23 is equal to 0 and this 41 0, right. So, then the work done is total work done or the net work done, right. This is your net work done, right, is nothing but RTH ln V2 by V1. We have already derived this, and the Q34 is nothing but RTL ln V4 by V3, right. So, if we will apply this, that we know thermal efficiency is nothing but your W net divided by the QH, and what we will do, we will just put these values, net, this is the work net here, I am like this is nothing but that and divided by the QH, which is nothing but RTH ln V2 by V1. And we can if you look at this divided, this and this term will be is it divided, then it will be 1, and then I can write down the efficiency, thermal efficiency is basically is 1 minus TL by TH, of course RR will cancel it out, into ln V3 by V4 divided by ln V2 by V1. So, this is the thermal efficiency for the Carnot engine, right. Now, what we will do, we will try to look at this, how we can relate this term, this ln V3 V4 and this term, and see that how we can relate this thing and see whether we can simplify this expression for the thermal efficiency. So, we know that for an isentropic process, right, we will be considering the process isentropic between station what you call 2 and 3, this is isentropic process, am I right? And similarly 4 and 1, these are isentropic process, right. And we know that for isentropic T V gamma minus 1 is equal to constant for an ideal gas, we have already assumed ideal gas in that. So, then I can write down between station 2 and 3, right, station 2 and 3, I can write down T2 V2 power to the gamma minus 1 is equal to T3 V3 gamma minus 1. And then we can rewrite that because the T2 is nothing but your. So, if you look at T2 is nothing but your what? T2 is TH, right, and T3 is TL. So, I can get this thing, that means basically TL by TH, I will take this denominator, and then that will be equal to V2 by V3 power to the gamma minus 1. Right. And in the similar way, we can also for the derive the similar expression for process 4 and 1, and that is nothing but TL by TH is equal to V1 by V4 power to the gamma minus 1. So, this expression and if you look at this equation 2 and 3, what you will see? You will see that both are TL by TH in the left hand side, both the equation. That means that we can write down V1 by V4 is equal to V2 by V3. What we will do, we will basically rewrite that expression. We can take this here and bring this over to here. I can write down the V3 by V4 is nothing but equal to V2 by V1, and then we can say that from here that this can be cancelled out, this is can be cancelled out because both are same, V3 by V4 is equal to V2 by V1. So, therefore, I can say that the thermal efficiency of the Carnot engine is equal to 1 minus TL by TH, right. This is a very simple formula what we got, that is basically it says the maximum efficiency what a engine can achieve, that is stipulated by the Carnot engine. So, and what it says, it does not depend on the fluid what it is, it will be dependent on the temperature of the source and the sink. The thermal efficiency will be not dependent on the what matter you are having and what it is, it will be only depend on the temperature of the source and the sink. So, that you should keep in mind, because we will be using this concept what you call very often to derive something. So, therefore, the Carnot engine is basically can have the maximum efficiency what a heat engine can attain, because it is a reversible engine, like if it and always irreversibility will be there in the system. So, therefore, I mean one cannot really go beyond a reversible engine. So, that is why the Carnot engine is having the maximum thermal efficiency. So, we will take an example like a gas turbine engine, let us say operated between temperature of 1200 Kelvin and temperature of 300 Kelvin. That means, if you look at this is your what you call source temperature, right, from which it is taking the heat, and this is the sink temperature, right. So, which the heat being rejected by the engine, and what will be its efficiency then? Its efficiency will be basically 1 minus 300 divided by 1200, that will give you 75% efficiency. Of course, if you could achieve in real sense this kind of order of efficiency for a heat engine, it will be great. So, from this one can really say that no heat engine can be more efficient than the Carnot engine operating between the same two thermal reservoir. That means, one is source, other is sink. If a heat engine is being operated, right, and that engine can never be have a higher efficiency than that of the Carnot engine, which is operated between the same temperature sources and sink. That means, so therefore, that is the Carnot theorem 1, and there is another also theorem which is little differently told. All reversible engine operating between the same two thermal reservoir have the same thermal efficiency, right. So, this is known as Carnot theorem 2. So, we will look at whether it is true or not by using the deduction method. So, we will do that now. So, let us assume that Carnot theorem is not correct, right, that we will do. That means what? That means basically what you call, there is a heat engine, right, which is having the higher efficiency than the Carnot engine, right, which is operated, both are operated between the two temperature source and sink. So, let us say there is an irreversible engine, that means most of the engines whatever we use is irreversible engine, right, and it is taking certain amount of heat, that is QH from a source at temperature TH, and it is rejecting certain amount of heat Q to the sink which is at TL and producing certain amount of work done, that is WIE. See, this IE is basically irreversible engine. And let us consider another of course, reversible engine which is taking the same amount of heat that of the irreversible engine from the same source, and it is of course rejecting QL amount of heat to the sink. In case of irreversible, it is Q, okay, it is not same, and it is producing the work done, that is the reversible work done. And let us assume what we will be doing, the efficiency of the irreversible engine is greater than the reversible engine, right. We are assuming that, means we are saying that Carnot theorem is not correct. So, therefore, the efficiency of the irreversible engine should be greater than the reversible engine. What is the meaning? Meaning is that basically by the efficiency we know that work what you call irreversible work done by the irreversible engine divided by the amount of heat which is absorbed from the source is greater than the what you call the thermal efficiency of the reversible engine, that is nothing but the work done by the reversible engine divided by the QH and QH. So, QH is being same, therefore, we can say that the work done by the reversible engine will be greater than the work done by the reversible engine, right. And this is we can say from this assumption and also from this deduction, right. Now, what we will do? We will just because the work done by the irreversible engine greater than the reversible engine, let us say that this work will be given to the reversible engine. As it is a reversible engine, it can operate other way around in the sense it will be taking QL amount of heat from the sink, right, and giving QH amount of the source, and this is a basically a refrigerator, right. This reversible engine is not a reversible, it is a refrigerator, right. Yes or no? Can I not do that? With a reversible engine, I can operate on the reverse way. Yes or no? Right? Possible. So that what will happen? I will join together. That means whatever the heat is given by this what you call a refrigeration system, QH, instead of giving here, I will divert this QH to this place, engine, so that it will go, and look at the whole system, right. And instead of giving this Q, and then it will go to the QL here. So, that what will be happening? That means this will be right. So, this QH and how much work will be when you join together this one and make one system to operate, that when the both irreversible engine and the reversible engine, that is basically refrigeration, operate in a single cycle. What it is saying? It will be basically taking the QL minus Q amount of heat from the sink, right, and it will be producing this amount of work done, that is WIE minus WRE, right. So, it violates what? It violates the Kelvin Planck statement, yes or no? That means it is taking basically certain amount of heat QL minus Q, and that is the net work, which is nothing but Wi minus WRE, it is being produced. So, therefore, the as I told that this combined system now is violating the Kelvin Planck statement, right. So, therefore, that assumption what we have made is not correct. That means that irreversible engine efficiency can be less than equal to the reversible engine, right. In other words, the reversible engine efficiency will be greater than equal to the irreversible engine. That is another way of looking at it, because that is not correct. Therefore, this will be maybe possible, right. And so, if you can look at that, like one can also argue by saying that like it will be reversible engine always will be greater than the irreversible engine. That means, the thermal efficiency of the reversible engine will be greater than the thermal efficiency of the irreversible engine. Therefore, Carnot theorem is correct. So, let us look at the proof of the Carnot theorem 2. That is what we we know that according to the Carnot theorem 2, all reversible engine operating between the same two thermal reservoirs have the same thermal efficiency. Right. What we will do now? We will say that let us consider a reversible engine 1, right, which is observing certain amount of heat, that is QH, from the source and rejecting certain amount of heat Q to the sink while producing the what you call certain amount of work, that is WRE1 by the reversible engine 1. And there is another reversible engine 2, which is taking the same amount of heat from the same source as that of the reversible engine 1, but however it is rejecting QL amount and it is producing different amount of work, that is WRE2, right. That is the we are considering. And we are saying that let us assume this Carnot theorem is not correct. What is the meaning that means? That means let us assume that the thermal efficiency of the reversible engine, right, is greater than the thermal efficiency of the reversible engine. We are assuming that. Then we know the thermal efficiency of the reversible engine, basically the ratio of the reversible work done by the engine 1 and the amount of heat being absorbed from the source, which is greater than the work done by the reversible engine 2 divided by QH. That means basically the WRE1 is greater than WRE2. And let us what you call operate this reverse engine 2 in a reverse cycle. That means it will be operated as a refrigerator system, right. So, what will happen? It will be taking this QL amount from the sink and you are giving some amount of work input, that is WRE, and this refrigeration system, which is the earlier it was a reversible engine, now it is acting as a refrigeration system. So, it will be giving the QH amount of heat to the source. So, what we will do? We will basically again combine it, this QH, whatever it is going to the source, I can divert this thing to the what you call this reversible engine 1. Instead of taking this QH from the source, the reversible engine 1 will take from the reversible engine 2. And similarly, you are rejecting this amount of heat, I can give this heat to the what you call QL instead of to the sink, or I will be giving this Q amount of heat which will be to this reversible engine, sorry, this refrigeration system. So, this we can say that the reversible engine 1 and the refrigeration reversible system basically will be the new cyclic device. So, then what will happen? Like again, if you look at, it is absorbing the QL minus Q amount of heat from the sink and doing the certain amount of work done, that is WRE minus WRE2. That means, whatever heat being taken from this sink is being done by this combined cycle, and which violates basically what you call the second law of thermodynamics, right. So, therefore, we call that basically the thermal efficiency of the reversible engine 1 cannot be greater than thermal efficiency of the reversible engine 2, because both are operating at the same source and sink. That means, it can be other way around, that what you call reversible engine 2's efficiency, thermal efficiency is greater than equal to the reversible engine thermal efficiency 1, right. So, by the similar arguments we can also prove that that this is also not correct, that is the thermal efficiency of reversible engine 2 cannot be greater than the thermal efficiency of reversible engine 1. So, by the similar argument it can be proved. Therefore, we can say that thermal efficiency of reversible engine 2 is equal to the thermal efficiency of reversible 1, which are operated between the same source and sink. So, as I told you, I mean this what you call theorems and also the Carnot engine indicates that thermal efficiency does not depend on the type of working fluid, rather it depends only on the temperature of the reservoir between which it operates. So, let us look at the Carnot engine further. I mean like let us say that the source it is the heat engine which is absorbing QH amount of heat, and then it is rejecting QL amount of heat to the sink, and it is producing a certain amount of work. So, any heat engine the efficiency will be basically 1 minus QL divided by QH, right. Okay. This is for any heat engine, it need not to be reversible, right, but for the Carnot engine which is a reversible engine, we have seen the thermal efficiency is basically 1 minus TL by TH. Okay. So, if I consider there is a same source, right, and there is a what you call a irreversible engine, right, which is taking a certain amount of heat QH and it is giving the same amount of QL, and it will be producing some amount of work done, right. Let us say this is WIR, IHE, let me write down irreversible heat engine. So, if you look at the efficiency here, what it would be? This thermal efficiency in this case, if it is a reversible engine, if I say this is a reversible engine, what will be thermal efficiency? Something 1 minus what you call 300 divided by 1200 is nothing but your 75%, right, is not it? Thermal efficiency 75%. Now, this efficiency for the irreversible engine, what it will be? Will it be less than 75% or greater than thermal 75%? It will be definitely less than 75%, because it is irreversible engine, right. It cannot be greater than or equal to the 75%. Okay. But let us consider that there is a person who claims that there is a engine which is does the same thing, observe the same QH amount from the same source and QL, and engine that which claims that that efficiency is thermal efficiency something 85%. If it is 85%, that means it is impossible to have any heat engine which will be have higher efficiency than that of a Carnot engine, which is a reversible engine. So, therefore, no heat engine can have higher efficiency than a reversible heat engine operating between the same high or low thermal reservoirs. So, to summarize that that means the thermal efficiency is same as that of a reversible engine, right, of any heat engines it will be same, and if it is thermal efficient engine for irreversible heat engine it will be less than that, and of course, it is not possible to have a heat engine which will be higher than the Carnot thermal efficiency, right. So, with this we will stop over and we will take few examples in the next lecture and then discuss about that, okay, about how to apply and other things.